Okay, now let's talk about some of the problems of our pipeline design. So one problem we have already talked about it. So some instructions require 5 stages, some require 4 stages. So occasionally, in the same clock cycle, different instructions may need to use the same hardware. That will cause some conflict. Okay, so we have already mentioned that already. So let's look at that first. Let's call structural hazard. So that's the conflict of use of a resource. So it maps pipeline with single memory for both data and instruction. So both load and store requires data access. And okay. Oh, okay. So basically, here we are talking about that we separate the. That's why we separate the data memory, instruction memory. Right, so for instruction decode, for instruction fetch, we use the instruction memory. For load and store, we use the data memory. And so we have separate components here. All right. So R-type takes only 4 stages. It doesn't need to go through the memory access stage. So let's look at our, if we have one load instruction followed by an R-type instruction. Okay. So load instruction needs to go through the entire 5 stages. But R-type instruction only takes 4 different stages. So in this example, at the 7th clock cycle, which is the 5th stage of the load instruction, so you need to do the write back. But at the same time, this R-type instruction also at its 4th stage, which is write back. So we have some conflict here. So this is what we call the structural hazard. 2 different instructions, they try to write to the register at the same time. But so that's problematic. So how to do that? So to avoid the structural hazard, we use a very simple strategy. We force each instruction to go through the entire 5 stages. Okay, so we force each instruction to use the same stages. So that means, so of course the load instruction needs to use the entire 5 stages. But the R-type instruction, although originally we say that at the 4th stage it will doing the write back, but now we sort of force the R-type instruction also needs to go through this memory access stage. But in fact, R-type doesn't need to access the memory. So this stage is sort of like idling stage. It needs to go through that stage, but it's sort of like it's doing nothing at that stage. But after such a simple modification, when we have a load instruction followed by a R-type instruction, so in this case, at the 7th clock cycle, when the load is processing the write back stage, this R-type instruction is in the memory access stage. Okay, so there's no structural hazard in this design. Although we sort of increase the response time for the R-type instruction, but because of pipeline, perhaps the throughput still improves. Okay, so that's the first sort of like, well, again, this is a workaround. This is somehow we try to fix the issue. So that's a workaround, but that's doable. All right, so now every instruction has to go through the entire 5 stage. That's our first fix. And let's think about store. Store also requires only 4 stages, right? It needs to go through instruction fetch, instruction decode, execution, memory access, but it doesn't need to do the write back. But in our design, again, because we force each instruction to have 5 stages, so it also needs to go through this useless write back stage. BEQ. BEQ only need to go through instruction fetch, instruction decode, execution. Execution is used to compute the target address. Okay? And then it doesn't need to access the memory. It doesn't need to write anything back to the register. But again, we force it to go through all 5 stages, although the last 2 stages are useless for BEQ. Okay, so so this is showing like if we have these instructions at different clock cycles, each component is used by which instruction. Okay, so in the first clock cycle, low word is using the instruction. Low word is in the instruction fetch stage. Okay, so it is using the instruction memory. In the second clock cycle, the first instruction is using the register. And the first instruction is using the instruction memory to do the instruction fetch. At the third clock cycle, at the third clock cycle, the first instruction is using the ALU to do to compute the target address. Simultaneously, the second instruction is in the instruction decode stage. Okay, so it sort of allocate all the registers. Simultaneously, the third instruction is using the instruction memory to fetch the instruction. Okay, at the fourth stage, well, let's look at the 5th stage directly. Okay, at the 5th stage, when the first instruction is writing something back to the register, the second instruction is doing nothing. Okay, so at the 5th clock cycle, the data memory is in fact, no one is using the data memory. But because we want to fix the structural hazard, we still require the sub instruction to go through this stage. Okay, likewise, in the 6th clock cycle, this R type instruction, although it is in its 4th stage, it's not using the data memory. Okay. Okay, so let me ask you a quiz. What is the ALU doing during the clock cycle 4? Okay, so you just check the table. Clock cycle 4, ALU is doing the second instruction. It is trying to subtract $2 and $3. Right? What is the data memory doing during clock cycle 5? Okay, clock cycle 5, data memory is in fact idling. Okay. All right, now let's look at a pipeline example inside the CPU, which means that now we want to really execute multiple different instructions simultaneously using a pipeline version CPU. Okay, so we are doing, let's see, I think we are doing these 5 different instructions inside the CPU. Okay, so first is low word. Low word, $10, $20, $1. Okay, so we read from PC, we read an instruction from the instruction memory. That's it. That is the machine code of this instruction. And we store the 32 bits inside this IFID register. And you will see PC equals to PC plus 4 and then saved back to PC. So in the next clock cycle, PC is increased by 4. Okay, so in the next clock cycle, PC can retrieve the new instruction. And now, the low word is here. So based on the 32 bits, the leftmost 6 bits, the CPU knows that this should be a low word. So it sets the control signals to their proper values. And then here will be RS. So let me try to write down. So the RS will be, in this case, it will be dollar sign. Well, it's hard for me to write, so let me just tell you. This will be $1. Okay? This RT will be $10. Although it will not be used later, but it will still have some value here. Okay, it's $10. Here, the right register, although it looks like it should be $10, right? But why is it gray out? I will talk about this later, but let's just presume that here should be $10. Although, like in a real design, it will not put $10 right now, but I will tell you why later. But for now, let's assume that it's $10, just for a minute. All right, and simultaneously, we will put the immediate field here at doing the sign extension. Okay, so the result is stored here, and here we will store the value in RS and RT. They are all stored here. Okay. In the next timestamp, oh, here we only have two instructions. Lower. Oh, okay, we only have two instructions. Okay. So in the next timestamp, now here is the value of RS. Here we have the value of RT. Here we have the value of immediate field. All right. And because of the control signal, we will let the immediate field to go inside to be the second input of the ALU, and compute the result and store the result in this register. Simultaneously, here, based on the OP code, it knows this is an R-type instruction. So here we have RS, RT, and RS, RT, and RD. Again, why is it gray out? I will tell you in a minute. But for now, let's assume that we put RD here. Simultaneously, we will also put the immediate field here, although it will not be used later. But for now, we still put immediate field here. All right. In the next clock cycle, we have, for the low word, we have already computed $1 plus 20. So we know the target address. So we go to the data memory to retrieve the data we want and put the result in this register. Simultaneously, here we have the $2, the value in $2, and we pass the value in $3 and compute the subtraction and put the result in this register. In the next clock cycle, now we already retrieved the data in the data memory. So we write the result back to the register. Okay. So here I will tell you, now I tell you why we didn't put the right register a couple of clock cycles earlier. Because if this is really a pipeline version, then perhaps here we have another instruction, say add RSRTRD. Right? We have another. So if we put the RD in this stage, then in fact we are storing this value to a wrong register. So we want to write the result to $10. So the right register is, in fact, we need to. So here we have this $10 is put into the right register in the right backstage. Does that make sense? So let me write it down to make it extremely clear. Let's say Okay, let's say if somehow at the 5th clock, the second stage, this instruction is in its second stage. So if we put this $5 inside this write register, then something goes wrong, right? Because it becomes like we load the word to $5. So that's wrong. So that means at the instruction decode stage, we should not put the write register yet. We should decide the value of the write register when we are doing the write back. Okay, so let's reword a couple of clock cycles. So in fact, in the low word, when the low word instruction is at its second stage, when we know that the RT field is 10, we should put this write register also in the memory here. Also in the register here. And in the next clock cycle, it is this $10 is also passed to this register. At the next clock cycle, this $10 is also passed to this register. So at the write back stage, this $10 can be passed back to this write register. And that's the write register. That's the RIGHT, WRITE, that's a write register. That's the correct write register. Let me put it this way. That's the correct write register. Does that make sense? All right. So in the next clock cycle, when this second instruction is doing the write back, again, this $11 is stored in this register. Okay, so this $11 is put back to this write register here. And now we know that the subtraction of these two registers is stored to $11. All right. Oh, okay. So this is just what I said. Okay, so why we didn't put the write register at the decode stage here? Because that's probably the wrong register. After a couple of clock cycles, that's already the wrong register. So we put the write register field only when we need to do the write back. All right. What else? Okay, so here we also miss a couple of things. So depending on whether we are dealing with R-type instruction or load instruction, sometimes the write register should be RT. Sometimes the write register should be RD. So in the instruction decode stage, because we haven't decided yet whether the destination, whether the write register should be RT or RD. So we store both RT and RD in the register. And here, after the instruction decode, we know that this is an R-type instruction or a I-type instruction. So we know if that's an R-type instruction, the write register should be RD. If that's a I-type instruction, the write register can only be RT. So here we have a mux, which decides, based on the control signal here, it decides if we need to write something to register, should that be RT or RD? Okay, so this one is used to decide whether we need to we need to use RT or RD as the write register. All right. What else did we add it? Oh, okay. And here we have a branch instruction, right? But we have a branch. So, although previously I said that, just perhaps in the last hour, I said that BEQ requires only 3 stages. instruction fetch, instruction decode, and the execution, which is used to compute the target address. Oh, I'm sorry, I said something wrong. Sorry, let me say that again. BEQ, instruction fetch, instruction decode, and the execution is executing whether RS equal to RT or not. So it's actually doing RS subject RT. But where is the target address? We still need to compute the target address, right? So in this design, although we will modify it again just in a minute, but now it computes the target address and RS subject RT simultaneously in the third stage. So here this ALU here is computing RS subject RT, whether they are equal or not. At the same time, this adder is computing the target address. Okay, so the target address is stored in this register. And if somehow RS indeed equals RT, this will be the next PC. Okay, does that make sense?